we're talking about some review questions. The first one will be about superconductivity. We haven't gone into it very much, but the general idea is that you have different classes of materials going from insulators, where their electrons in the insulator are confined to sort of energy states, which are separated from states in which they can move very well. So you have your insulating state, and then you have those electrons that are present are in some filled band, which originated from some atomic level, just was spread out, but there's a large gap in energy units, sort of the order of anywhere from one, well, I don't know, let's say 5 to 10 electron volts. An electron volt is the amount of energy an electric charge, the elementary electric charge, picks up in 1 volt drop, and it has energy. You see, a charge is 1.6 times 10 to the minus 19th coulombs, and a volt is a joule per coulomb, so that an electron volt has an energy equal to 1.6 times 10 to the minus 19th joules. Now, one of the things that you might be good to be familiar with this, how much does this represent? For example, what is the corresponding frequency that such a energy represents? For example, if I have an energy gap of 1 volt, 1 EV, what frequency does it take to excite across that gap? What is the energy of a photon that is necessary here? That's a good thing to know, or to be familiar with. Or let's put it this way, not to be scared of, at a minimum. Or another thing that you might be interested in is how much temperature does it take, kT, kBT, to excite across an energy gap? In other words, when is kBT equal to an electron volt? It turns out that the temperature there is around 12,000 degrees Kelvin. That one I remember. The frequency here is something like 10 to the 14th cycles to get that energy. So an electron volt represents a sort of energy on our scale. Yes, sir? That's the energy of 1 electron volt. If the question, you see, these are all energies, but they kind of they relate to each other. In other words, for example, what I'm saying here is suppose I had an energy gap of 1 electron volt. How much temperature would it take to excite across there? So when is the energy to 1 particle, kBT, is the energy going to 1 particle? How much temperature would I need to likely get a transition across? And it turns out to be very high. I won't go into this too much because it's late in the course at the end. But it actually, see, a volt is like a volt. The battery I just put in is maybe 9 volts or something. But what we're accustomed to, it's kind of energy on our scale. Our chemical bonds are probably in the order of, what, fractions of an electron volt. Light is the order of a volt. Our visible light. We live in sort of, our world is sort of volt-like world. And the fact is that that frequency is roughly the frequency of visible light, which is also, you know, remember the hydrogen atom? The energies in the hydrogen atom are like 13 electron volts. The next level was minus 4 electron volts. So it's in around there. So the transitions that we are accustomed to dealing with are sort of in the volt range, which is really very good because it means that we can get things like laser pointers that are visible from batteries. In other words, if you can get an electron up 1 electron volt above some level and have it drop down, it will shoot out light in our visible range. And that's great. That means you can just plug a battery into a device, a laser, a solid-state laser, and get light. So it's just interesting to notice that the volt is the range here, but the thing is that it takes a very high temperature to get a volt, which is a good reason why we're lucky that we can use sort of quantum effects to get light, like diode lasers, just a volt or so. But anyhow, I just want to put that in scale here. The point being that if the gap is sort of in the range of 5 and 10 volts, that requires huge temperature to get an electron to jump from here to here. So that doesn't happen. So what you need to get thermal excitation, the gap has to be sort of less than a volt. Now silicon is 1.1 volts, we said, and even that has very few carriers. So the way we beat that, so we go from insulator to semiconductor, and that's not even a very semi-anything really. Silicon is very, very poor because that gap is too great. At room temperature, remember that room temperature, Kb 300 Kelvin, is only a 40th of an electron volt. So that's another unit, another consequence. So at our temperatures, we have a 40th, way less than 1 volt. So it's very, very small excitation possible in silicon. So we beat that by doping it with various impurities, which are much closer, such that Kt is 40th at room temperature, can release carriers into the bands. Okay, so that's insulators, semiconductors, and then doped semiconductors. I'll give you a quick review. The other category of material is the metallic conductor, where you have a band which is partially filled, for example, so that electrons can pick up energy from the electric field, and they can move within this unfilled band. It's like a highway with 2 lanes, and there's only 1 lane filled. You can always go into the other lane to travel fast. And this can happen because the band is unfilled, or because you have a filled band, but you maybe have a second band which overlaps it, so they can go into the frontage road. Yes, I remember the word, frontage road, of the second band. This is a second band that happens to overlap. It's possible that this second band came from someplace, and this other band came from another original atomic state. You know, they developed. Okay, so the superconductivity is a class of materials within this metallic conduction group. Certain materials behave in a special way. Namely, if you plot, say, the conductivity of the material, this is how well it conducts, which, by the way, is Ne squared tau over m. So it depends on the number of carriers, the charge, the scattering, and the mass. In a typical material, as you lower the temperature, the conductivity will go down, and usually it levels off and flattens out. We understand why. In fact, it should be heading toward 0, but then it flattens out because of various impurities. So it's trying to go to 0. In other words, if the lattice stops shaking, the electrons can go through presumably perfectly. So the resistance, conductivity, oh, what am I doing it wrong. This should be resistivity. Go, if you pardon me. Yeah, let's make it resistivity. I'm sorry, folks. So that was right for conductivity, but the resistivity is 1 over the conductivity. And so let's say it's a little easier to see how it goes, resistivity versus temperature. So the resistance is going down. This is the resistance per cubic meter of material, right? Resistivity. So it goes down because the lattice is shaking less and less, and it scatters the carriers less and less. Then at some point, the thing tends to level off, you recall? This is a temperature effect. This is due to impurities, static impurities. Namely, things like, if you had a copper thing here, there might be a little tin in it, or some other kind of impurity, aluminum or whatever happens to, dirt that got into the material, but it's sitting there and it sort of impedes the flow of current. So you get this kind of leveling off, and it's not temperature dependent. The impurity is just sitting there, so you just run into it, can't help it. Okay, so that's, of course, you can do something about. Now, most materials just do this. This is the typical behavior of a metallic conductor. But there are these few materials which they do seem to be doing the normal thing. They seem to be heading toward 0, but then at some point they actually drop and go to 0 very rapidly. Or, well, you can smear it out a little bit, but they do end up at 0 resistivity as a function of temperature. This is called the critical temperature. And at that point, the resistivity is literally 0. So it's a special phenomenon which is understood pretty well in some materials, but not well in others. For example, we have the simple metals like lead, tin, and aluminum, where it happens. And we think we understand that fairly well. There's a theory that was done about 50, 60 years ago, which seems to account for those. But there's recent, in 1986 or so, a new class of material was discovered where this phenomenon occurs even better than these other materials, where the transition occurs at a much higher temperature than previously was observed. So it happens up here in those materials. Those they're called the high, or let me put it this way, high TC materials, high critical temperature materials. And they're very much being studied now because we're trying to understand why it happens. It's still understand. It's been now, 30 years or more? And for all our great brains, including a lot of people here at this university, trying to figure out why these materials become superconductors. We don't really understand this. A lot of questions about why this phenomenon occurs. But the basic phenomenon is that the electrical resistance goes to 0. And the other thing that these superconductors do is they don't allow magnetic fields inside them, except in peculiar ways. So if you put them in a magnetic field, the magnetic field will sort of be excluded. I haven't talked about that particularly. The basic resistivity phenomenon is that resistance goes to 0. And it's a wonderful thing if you can use it, because then you don't have the heating of wires. So I squared R losses that we talked about, the power in a resistor, it uses up some energy. In a superconductor, it doesn't. So if you can, well, by the way, these temperatures are pretty low. So the typical, for example, the first one that was discovered was, I think, mercury. It was around 10 Kelvin. You see, these early ones were in this range, 10 degrees above absolute. And then there's aluminum is down around 4. So this might be mercury, and this might be aluminum. And lead is around in here. Lead is pretty high, relatively high. Then there was some alloys. Niobium-3 tin, I think at one time was the champion of this class of materials, at around 20 Kelvin. But then this breakthrough in 1986, it's a whole different class of materials. And nobody suspected, except a couple of guys in Switzerland, suspected that these materials might be superconductors. And they found them. And they are typically copper oxide, like yttrium, barium, copper oxide, CuCO3 or something like that. It's rather complicated stuff, that very different from the ordinary metals. But you have to also be aware that a lot of metals don't become superconductors. It's funny, the good conductors don't become superconductors. It's sort of the bad conductors, like lead, tin, aluminum, the poor conductors. But gold doesn't, silver doesn't, copper doesn't, as far as anybody's ever found. You go down looking for this to happen, doesn't happen. Why does that? That's a good question. In those simple metals, we have an idea. And namely that the reason those are poor conductors is that it seems to be a good connection to the lattice, such that when you're a conductor, up in here, these are poor conductors because this temperature effect gets you. Now that's bad when you're up here, but it turns out that down here, what happens is that because the lattice is involved, the electrons somehow connect with each other through the lattice. They shake the lattice, and the lattice shakes another electron. So whereas electrons before were generally repelling each other, which are both negative, now because the lattice is well connected to in this particular material, the lattice grabs the electrons and they get to be attracted to each other. And by that means you have like a group, and it's hard to stop the group of electrons from traveling. So it's this electron lattice interaction which comes into play in the simple metals, like simple but how shall I say, poor conducting metals like lead. It's coupled well to the lattice. It makes the electrons then coupled well to each other. You get this group phenomenon. It's kind of a collective phenomenon, and it allows the electrons as a group to get through, whereas singly they don't. And what happens at the transition temperature is that the thermal agitation is enough to break up the group. And then if they're on their own, and they scatter badly. But when they're together, they have collective motion, and they are good superconductors then. The same mechanism was tried for the high TC materials, and nobody could really make it work. They just don't know. It's very complicated. There's sort of all kinds of stuff going on, which is very interesting, but it's a very good question. So that's a bit on that. Now, let's go to these couple of questions here, if we may. This one is about, this is problem 12 in section 17. Let's just see what, it has some nice physics in it, I think. I haven't looked at it in a while, but so it says a beam of electrons, and it shows a picture like this. These are electrons in a beam going up against a couple of slits. And there's a screen over here, and the two small slits are separated by a small distance, d, I guess. That's d, which is true. Now the question A is, decreasing the speed of the electrons will cause the first interference minimum to move further from the central axis. Which is true. Which is true. Decreasing the slit will cause it to move. One is further, one is closer. Each individual electron gets spread out as it passes through the slits, and little bits of each hits each intensity maximum on the screen. No electron will be detected on the screen at the central axis because they are blocked by the solid portion. Okay, so some of those I think we can throw out right away. I think that the hard one is the first two questions. I think. No electrons will be detected. That is not true, because these electrons, they're talking here about the wave nature of electrons, the de Broglie idea. Let's see. Yeah, we can look at it this way. The wavelength is given by h over the momentum, mv. And so that's what we're really dealing with here, right? We got that far. Okay. Now, the physics of what's going to go on is that each of these is a wave, and think of it as light. Each of these electrons is kind of like a wavefront, striking this, each of them separately. There's no particular correlation, I don't think, among these electrons. So think of every electron, but it's okay. Every one of them, if they have the same speed, they have their wave character, they'll strike this screen, and now we're dealing with an optics problem. The old optics problem, namely that you get a Huygens wave coming out of each slit. And the question is, do the waves, when they arrive at a point, do the waves from the different slits, this is one, so the point is that every one electron does that. So we don't say, part C said, every individual electron gets spread out as it passes through the slits, and a little bit of it hits the intended, well, it doesn't go into bits. It's just a wave. And indeed, you want to think of it as a continuous wave, and it's passing through, just like a light wave, it's passing through both slits simultaneously. This electron is passing through both slits simultaneously in its wave-like life, in its transmission life. And so it isn't though it's falling into bits. The electrons are breaking up into pieces and then reorganizing on the screen. Think of it as a wave. So number C is wrong. No electrons will be detected on the screen because they are blocked. No, because some of this wave can arrive here from each slit by diffraction. So this is a classic electron diffraction problem. And now the question really is, so C and D are not true. Decreasing the slit will cause the minimum to move in or out. In other words, the first minimum comes when there's a half wavelength difference. There's some place here where there's a half wavelength difference between the two parts of the wave passing through the slits. And when there's a half wavelength difference, this wave comes in, whereas this one might come in this way. This one is going to come in half wavelength out of step, and you get the minimum. Because you made them just, whereas one was like this, the other is by half wavelength, we mean it's just this opposite phase. This would be a half wavelength difference, and they will cancel, and then you get your minimum. So the question is, as you make the, if you change the speed, what will this minimum do? Now, when you change the speed, you're changing this v here, and it says what? Decrease the speed? Decreasing the speed. Decrease. So we make v less. So v is going to be less, which means that lambda is going to be greater. The place of this minimum is when n half wavelengths is equal to this extra distance, d sine theta. So it's just the optics problem. And we're saying the first minimum, so n is 1. So lambda has gone up, sine theta should go up, which means that this angle here, this is basically our theta. This should go up. That's what they're talking about. Okay? And, now we have your problem, which is, see, thank you. That's a good question. I think I got knocked out there. Okay, part of a treatment program, a patient ingests a radioactive pharmaceutical containing phosphorus to emit beta minus with an RBE of 1.5. The half-life is 14.3 days, and the initial activity is 1.34 million becquerels. How many electrons are emitted over a period of a week? Okay, well, this is a little harder problem. Okay, let's see. Okay. So let's put down, what are the symptoms of this problem? Beta minus, RBE is 1.5. I don't know exactly what is relevant. The initial activity, N0, or rate 0, might be better. Okay, let's call it the rate is 1.34 million becquerels. How many are emitted over a week? Explanatory answer. Well, the tricky part is that the activity is this actually is maybe beyond what I expect you guys to do. Namely, the fact is that the activity is going to go as e to the n0 2 to the minus t over the t1 half. Recall that? Right. So we're starting out with an initial activity. The problem with this, why this is a hard problem, is that it starts out at a certain amount, and it decays in, let me write down, that's another initial condition here of the problem. T1 half is